Continuing on talking about resonance, in this video we're going to focus on drawing resonance structures of some more complicated organic compounds. And this takes a lot of practice. It's something that you'll need to be able to do as you work through Organic Chemistry 1 and 2. If it doesn't come to you right away, don't worry, just keep practicing and keep working on it so that over time you'll become comfortable with drawing these resonance structures. So first we're going to go through our rules that we need to keep in mind when we're drawing resonance structures. There's a detailed page of notes on this on Canvas, so if you haven't looked at that already, I would recommend that you do that. So we'll just go over the rules and notes briefly here, but more detail is on that page on Canvas. So first, as I mentioned in the last video, in order for resonance to occur, we have to have that conjugation. So all of the atoms involved must have a p orbital. Second, the connectivity of the atoms stays the same. So only pi and non-bonding or lone pair electrons, as I typically call them, can move. Okay, so only pi and lone pair electrons move. Everything else has to stay the same. Also, the total number of electrons and the net charge have to stay the same. So we can't be adding electrons in or taking them out. Finally, we want to be keeping the octet rule in mind. So any of those second row atoms cannot have more than an octet. All right, 5 bonds to carbon is always bad. Hydrogen doesn't have a p orbital, and so it can never be involved in resonance. Boron, we typically won't see in this class, but carbon can have less than an octet. And when it has 3 bonds, it has a positive charge. All right, so that's something we'll actually see in our first example. Finally, we often will have formal charges in the structures that we're drawing. And our resonance contributors won't necessarily all be equal. So some of them would be more reflective of the structure, and others will be important to draw, but they contribute less to what that overall structure looks like. All right, so if we have a formal charge that's a negative formal charge, a more stable structure would have that formal charge on an electronegative atom like oxygen or nitrogen. Okay, so we're going to jump right into an example here. And first, let's analyze our pattern. All right, so here we have a pi sigma plus on carbon. Okay, so our p orbitals on this carbon here, this carbon, and this one. All right, so as we have this picture now, what we think about is this being a pi bond and this one being an empty p orbital because of that positive charge. Okay, so in our resonance structure, what we're just going to do is to keep our sigma bonding framework exactly the same. Okay, so that's a good place to start. Just draw all the sigma bonds exactly as they are. Okay? But then what we can do is to move our pi electrons here to the other side. Okay, so we could put the pi over there. And then when we do that, that leaves our carbon on the other end with only 3 bonds. Okay, so then that carbon gets the positive. Okay, so those are our two resonance structures, and what that shows us is that our positive charge is shared by both carbons on either end. Okay, so our resonance hybrid, typically we won't draw these, but sometimes it can be helpful, would show, again, we keep sigma bonding framework exactly the same. This is our hybrid. So this has partial double bond character, partial positive on this carbon, and partial positive on this carbon. All right, so I'm also going to show you something else that is a kind of staple of organic chemistry. And that is, sometimes it's helpful to have a way to keep track of where the electrons are coming from and where they're going to as we draw these different structures. And we do that using an arrow. Okay, and it's a curved arrow or curly arrow. Okay, so our curved arrow shows where electrons go. All right, that red is not showing up too well. So we'll do blue. Okay, so what's going to happen is we'll have some electrons, lone pair, pi bond, and our arrow will start there. Okay, and then the head of the arrow is going to show kind of those electrons are flowing into a new position. So they're going to stay attached on one side and then reattach in a new place on the other side. So we can draw that for our first resonance structure here to help us see how we get to the second one. Okay, so these pi electrons that are moving, we're taking the pi electrons here, our arrow starts there, and it goes here, okay? And we're going to form a new pi bond here, all right? And see how those electrons that we moved when we get to the second structure, they stayed attached to the same carbon on one side, but now they're attached to a new carbon on the other side, okay? So that we can use that arrow to show that. And we'll be doing a lot more practice with showing how those arrows demonstrate the flow of electrons. Okay, here's another example. And this one getting a little bit more complicated. So we have our plus sigma pi, but then we also added a second part. So sigma lone pair. So our first resonance structure will be essentially the same as what we drew above. So we just switch the locations of the pi bond and the positive charge. But now that we have a lone pair, I'll redraw this a little bit. Okay, so remember, if we have a lone pair, have one lone pair that's not involved, but another lone pair that's in a p orbital, okay? So that it can be part of that conjugated system for the added stability. So what we'll do is we'll take that lone pair in the p orbital and push it toward, toward the positive, okay? So it starts as a lone pair, then it's going to go to help fill that carbon empty orbital. So it's going to end up as a pi bond. So by doing that, now we have a full octet on that carbon, has 4 bonds. We have 1 lone pair on oxygen, that wasn't involved. So now we kept our octet on oxygen, but it has 3 bonds instead of the normal 2. So that's going to give it a overall +1 formal charge. Okay, so those are our 3 resonance structures for that example. So in this case, we have pi sigma lone pair sigma pi. Okay, so again, this is a longer system. And if we have a lone pair, if we have this pattern lone pair sigma pi, it's usually a good idea to start with that lone pair. All right, so in this case in particular, we have carbon with a negative charge. Okay, so carbon has an octet. It has the lone pair, that's 2, bond to hydrogen, 2, and then the 2 bonds to carbon, so that gives us a total of 8. But it also has a negative charge, so it has more electron density around it than it really wants. So we're going to start by taking that lone pair and pushing it toward our sigma, okay, to make a new pi bond here. All right, but when we take that lone pair and make it to a pi bond, we also have to move something out of the way, because if we just did this first step, then we end up with 5 bonds to this carbon here. That would be bad. Okay, so what we want to do at the same time is take our pi bond here and make a new lone pair. Okay, so we're actually we're just switching the pattern. Okay, so nothing happens here. We can just draw out our sigma bonding framework. All right, and then start to fill in. So we didn't do anything on this side yet. Over here, we still have our 2 lone pairs. Okay, so what we did was to make a new pi bond here and a new lone pair here, right? And we also put the negative charge onto that oxygen because now it has 3 lone pairs and 1 bond, all right? So that corresponds to negative formal charge on oxygen. All right, and then we can do the same thing on the other side as well. So again, if we just keep our sigma bonding framework, just draw it the same every time. Okay, so this time we'll keep everything the same on this oxygen, and we'll make our new pi bond on this side, negative charge and lone pair on the other oxygen. One thing to keep in mind, so a very important rule for resonance structures, is that we're only involving the atoms that have a p orbital. So these carbons on the end are sp3 hybridized, no p orbital, so these are not involved in the resonance. Okay, and then another thing we can do here is to rank the importance of the resonance structures that we drew. All right, so we can see that our negative charge is shared by our central carbon and then the two oxygens. So having a negative charge on oxygen is better because it's more electronegative, okay? So we can say that if it's on oxygen, that's a major resonance contributor. And these two are equal. Because they both have that negative charge on oxygen. All right, and then the first one that we have here, that will be our minor contributor. Minor. Because it has the negative charge on carbon, which is less electronegative, so it's not as stable. Okay, so one more example here. Here's a problem that you might see. Determine whether the following pairs are resonance structures or not. If not, explain why not. If so, determine whether one contributor is a major contributor or whether both are equal. Okay, so if we look at our first molecule here, we see that pattern of pi, sigma, pi. We might also want to draw in the lone pair electrons since they weren't given. Okay, so those 4 atoms have the p orbitals. Those double bonds are the conjugated electrons. And so what we should see in a resonance contributor, a resonance structure, is that those electrons are shared between the same 4 atoms. All right. But what we actually see over here is that this pi bond has moved outside of those 4 atoms. Okay, so remember that this was sp3 hybridized, so not involved in resonance. Okay, so if our double bond moved to that position, that means that this is not a resonance structure. All right, we broke a cardinal rule by moving our pi electrons toward an sp3 hybridized atom, and in the process we also switched the location of one of our hydrogens, right? So this has CH3, this is CH. In our second one here, we have CH2 and CH2, all right? So we moved a hydrogen, not allowed for resonance structure. All right, and actually our product over here is not conjugated. Not conjugated. All right, because we have pi, sigma, sigma, pi. So we have this sp3 carbon in the middle that acts as a block so that the p orbitals on the 2 separate sides can't overlap with each other. Okay, so these are not resonance structures because we actually changed the underlying sigma bonding framework of our molecule to get to the second structure.